4.1 continued, finding local max and mins. So basically what we want to be able to do is look at a function. We know what they look like, basically. It's one that, there's a peak and a valley or whatever. But it may not be smooth. Maybe a corner or maybe a cusp. So this is what we do. So take a look at this kind of picture. I'm going to just copy this once I draw it. That way it'll be all the same. So you have some function maybe like this. And right about here is your local maximum. So you can put an interval around it like this. And that's, of course, your local maximum. So what's happening then is we can see that as you go from left to right, you can look at these tangent lines. So the slope of the tangent line is positive here. And then as you go down the other side, the slope of the tangent line is negative. And then what's happening at the very top? So right at that value, what's the slope of the tangent line? It's right there. We can see that f prime of c is equal to 0. The slope is 0. So that's an important value, important concept. Similarly, I forgot to copy the coordinate system over. Oh well, not hard to draw. You could have a local max that looks like this. So it doesn't have to be nice and smooth like that. Another case might be something like this. The graph could come up like this. So let's suppose it did this. It could be like this. And then come back down. I meant for it to just basically do that. So graph could just go like that. What's that called? Anybody know what that's called? That's called a cusp. Okay, so the graph could do that. So that's also an important value and is a critical value. So at C, that is still a local max. So that's a local maximum as well. This is a local max. Minimum would just be reverse of that, essentially. So both local max. In this case, the slopes basically approach infinity. So if you take a line, I have to erase these, but if you take a slope, it goes like this. This is really steep. And then it starts going like this, and it starts going to infinity, approaching infinity. Okay, and from the other side, it's negative. So in this case, what we say is f prime does not exist. So we look for those cases. So both are local max in that case. So those are important points. We call them something. Those are called critical values. Oops. So here's the definition of a critical value. Very, very important. So definition, let me just write it out. This is the definition of a critical value. Sometimes you say critical point, even though it's not an actual point. It's just one value, but kind of use them interchangeably. Definition of a critical value is this. So we let f be defined at C and then you have two cases. If f prime of c equals 0, or f prime of c does not exist, like approaches infinity or negative infinity. So that's this case, of course, here. This is a D&E case. So, are both these functions continuous? Right, look how I drew that. So is that continuous? Is this continuous? Yeah, both are continuous. But the function is not differentiable here. Remember? So differentiability. So continuity does not imply differentiability, which is not at C. It is not. We would say the function f is not differentiable here, but the function is differentiable everywhere else on this graph. So differentiability implies continuity, but not vice versa. Remember that theorem? Important theorem. But that is a critical value, and it may be a local max or min. Okay. So then C is a critical value. So if f prime of C equals 0, or f prime of C does not exist, then C is called a critical value. And I suppose we could say f of C is a critical point. So we have to list these things out. So what I often do is I have you label them. So we want to label those things. Let's make it like pink or something. This is a critical value, CV. Critical values, list them out. The point would be maybe the y value too. You can say critical point, but I like to call them CVs because that's what you're going to list out. And then we will test to see if they are local max or mins. It may be nothing. Okay, but that's what we're basically developing, is what is saying what. Okay. So here's another theorem. So this theorem states relative or local extrema occur only, that's critical, only at critical values. This is really important, is what I mean. Oh, I didn't spell that right. Only occur at critical values. So what we do is we find all the critical values of a function, and then we have tests to see if they are in fact local min or max. Okay, so that tells us where they are. It doesn't tell us how to find them. So basically, another way of saying this is this. So if f has a relative minimum or maximum at C, then C is a critical value. But not vice versa. Just because it's a critical value, like f prime is 0, it does not mean it is a local max or min. Okay, so the converse is not true. So be very careful. The converse is not true. Okay, so that's really important to know. Okay. So we have these different cases. So the critical values basically for C. So when it's a critical value, you have only two things. F prime of C is equal to 0, or F prime of C does not exist. That's it. So so this case, let me just show you the different cases again, concepts. This time I'm going to remember to copy that. Okay, so you have and I'll have one more to do, so I'll move it over as well. And I'm not going to have enough. Okay, well, you just bear with me. We're going to have to make this smaller. I need to fit all. I want to fit all three on the same grid. This happens in class too, so this is like nothing new. All right, so you have different cases. So I want you to have, this is for all, this is local max or min. So you have local max or min here. You could have a cusp. Let's go the other direction. Let's do this. Let's do this. So you could have a cusp coming down like this. And then you could have something like this too. And why not? Make it just like that is fine. Sometimes it just doesn't do what I wanted to do. That's a corner. So a corner is not local. So so the corner is not a cusp, and a cusp is defined very critically. So this, you have a slope here, which is different. You have that slope is different than this slope. Okay, so those slopes are different slopes. So f prime may not exist there. So that's a D&E. So f prime does not exist. But you need to see if it's a cusp. A cusp is they approach infinity on the right or left and right, or vice versa, left, right, or left, and then you get a cusp. So it only occurs on cusps that you get a local max or min. So those are not local max or min. So this is a cusp. We'll talk more about it as we do them. And this is a D&E. Okay, and this is a local min in this case. And this one has two local maxes. So, or I'm sorry, this is two local extrema. This would be a local max, of course, and this would be a local min. Okay, so finding extrema on a, so we want to look at basically the closed interval case for most of this. And this is finding extrema on a closed interval, what you do. I think this might run long. Let me see how much I just did here. Yeah, let's just keep going. Whatever, make it a half an hour, doesn't matter. Okay, so finding, this will help you with your homework stuff. Finding extrema on a closed interval. From A to B. Okay, so this is what you do. 1, find where, like calculate f prime is equal to 0, and or f prime does not exist. List the critical values, CV, right, critical values. 2, calculate f of a, right? That's the endpoint. And f of b. Calculate f of a and f of b. Those are the endpoints. And then you just compare values. So 3. Compare the values of 1 and 2. Meaning, whichever one's maximum, that's it. Whichever one's minimum, that's it. So that's all you're looking at. It must happen. You must get a max or min, and it could be the endpoints. So let's look at some examples of that. Okay, so this is an example that basically you get a critical value, but it doesn't. It is not an extrema. Let me see what the endpoint is. Okay. Sorry, I was looking ahead a little bit. I'll make sure it's what I wanted to do. So determine, this is actually a good question. Determine extrema or extremum on the interval -1 to 1 for f of x equal to x cubed. There's a very specific reason why I wanted to do this one. Just a forward-looking thing, concept. What are the zeros? Yeah, the zeros are just x equals 0. So it passes through x equals 0, right? Okay, just an FYI on that. All right, so what you do first, calculate f prime, right? So f prime, so a nice thing about this, you just start taking derivatives, is 3x squared. Okay, then what you do next is you set f prime equal to 0 and solve. That's like every time. You're going to do this for the next couple sections. Okay, so 3x squared is equal to 0 whenever x is equal to 0. You actually have a double root at 0 there for the critical value. So x equals 0 is a critical value. Okay. What about so one critical value is 0, is x equals 0. What about existence? So f prime exists on everything, everywhere, right? On the reals. So nothing to worry about for D and E's. Okay, so that's 1. So 2 is test endpoints. That's right. So test endpoints. So endpoints are f of -1. That's just -1. And f of 1 is just 1. Right? You're just cubing it. So then you just compare. I mean, basically all you're looking at now is you're comparing -1. Let's just change colors for fun. 1 and 0. All right, so when f prime is equal to 0, did that do anything? And you can see it doesn't. It's nothing. So we are just now comparing. I'll write it out. So f of -1 equals -1. That's the smallest, so that's absolute minimum. F of 0 is equal to 0. That's nothing. Well, it's not extrema. So we really should say not extrema. extrema. It is something we'll talk about later. So it's nothing yet, but really I'm saying it's not extrema, right? And then f of 1 is equal to 1. That is absolute maximum. So just keep in mind what this graph looks like. Okay, so your graph of the cube function does this. It goes steep, and then it goes flat right at 0, and then it takes off. So right there at 0, it's flat. So the slope of the tangent line is going like this, then this, then this, and then all of a sudden it's flat, and then it's this, and then this. So, but it is not a local extrema, so it doesn't have a max or a min there. So just because you get f prime is 0, you still got to see what's going on. Now we'll have ways to test for local max or min later. I think that's a little farther ahead in sections, but it just means that the slope of the tangent line is 0, which it does go to 0, but it doesn't mean it's anything. What actually happens though is the graph has like orientation kind of down like this, and this orientation is up. And actually, so see how that kind of works? This is kind of going down, this one goes kind of up. It changes right there. So in the future, that will be something that's called an inflection point. We get to that later. Okay, next example is this one. Okay, so another polynomial. So if f of x equals x cubed minus 12x, find the maximum and minimum on the closed interval from -3 to 5. So first thing you do is take the derivative, f prime, and you get 3x squared minus 12. And then right away, you just set that equal to 0. And you solve it. Factor out the 3. It's x squared minus 4 equal to 0. Continue to factor. 3 doesn't do anything, so you just divide it. And that's x plus 2x minus 2 equal to 0. So our critical values are plus or minus 3. I mean 2, plus or minus 2. All right, are those on the interval? Yeah, -2 and 2. So one thing to keep in mind is those are in the interval in question. Okay, so that's a yes, so that's true. So, I mean, you could have a critical value outside the interval in question, but those are. Okay, so we're good there. F prime exists everywhere. So nothing to worry about for D&Es. So now you just test everything. Test endpoints, so you do f of -3. I'll just tell you what it is. You just evaluate, you get 9. F of -2, evaluate, you get 16. F of 2, you evaluate, you get -16. And f of 5, the endpoint, you evaluate and you get 65. All right, so you just label them. Basically, this is absolute max. This is absolute minimum. So in this case, the critical value at 2 gives you an absolute minimum on the interval. This basically will be a local as well. We'll get to that later. This will be a local as well, but we'll get to that later. And then that's just an endpoint. Okay, so we'll talk about this. So this graph, let's see, this graph probably does something like this. Probably goes like that. So you got a max, min, and then we tested endpoints. That's probably what's going on. And we'll get to, again, that's later stuff, but we will be graphing all these things. Okay, last example. This one actually has a D and E. Okay, so find extrema of f of x equal to 2x minus 3x to the 2/3. Okay, what do we do here? On the closed interval from -1 to 3. So take the derivative, so f prime of x is equal to 2, then multiply, so it'll be just 2 minus x to the negative 1/3. So then you get minus 2x, and then so it's negative 1/3 when you subtract. Set that equal to 0 and solve. So you get 1 minus x to the negative 1/3, like that, equal to 0. And when you solve this, basically you got to mess with it a bit. Bring that down, solve, so you end up getting that this is equal if and only if we get 1 is equal to 1 over cube root of x. So that's true if x is equal to, so x can't be 0, that's undefined. But if x is equal to 1, it's a solution. So our critical values are x equal to 0 and 1, right? So f prime does not exist at x equals 0. So those are our critical values. Okay, so then you just compare. All right, I could have solved this a little further for you. I forgot to do that. Cube root of x is equal to 1. Cube both sides, x is equal to 1. All along, we have to say x is not equal to 0, which is when it's undefined. Okay, so that's how I got that. So now you compare. So f of 0 is 0. F of 1, 2 minus 3 is negative 1. F of negative 1 is negative 2 minus 3 is negative 5. F of 3 is equal to 6 minus 3, 3 to the 2/3. Simplify that, and we'll just get an approximation. So it's approximately negative 0.24, which is nothing. Nothing's there. So basically we have, this is the absolute minimum, and this will be the maximum on that interval, of course. Okay, so that's how you do it. But what we haven't done is, like, we want to graph these things. We're going to have functions that look like this, and like we have minimum, max, inflection points. So that's what we're getting into. Right now it's just, and this section is just the, on the closed interval, what's happening.